Hi guys, this is going to be the final video of the course. It's going to cover sections 8.3 and 8.4. When you're done with this, there is a homework assignment over it, and the final test is covering 8.1, 8.2, 8.3, and 8.4. The test is already available whenever you're ready, and there is no test review. Just this chapter was so short. And it's so close to the end, I didn't really see a need to go back and do new problems. But there is a chapter test review in the book with answers that you can use to prepare. And then, of course, if you have any questions, just let me know. All right, so we're going to go ahead and get started. We're starting with section 8.3 on page 533. The objectives for 8.3 is to add and subtract like radicals and to simplify radical expressions and then add or subtract any like radicals. All right. So example 1, adding and subtracting radicals is similar to adding and subtracting like terms. The same number must be under the radical, and the radical must contain the same type, meaning squared or cubed or etc. So we're going to start with our two example problems. All right, so starting with the first one, when I said that it's kind of like terms, notice we have the square root of 11 and the square root of 11, but the numbers in front are different. So the radicals kind of act like a variable in a way. If you have, say, 4x plus 5x, the x stays x, and then you're just adding the coefficients. So think of the numbers in front of of identical radicals as coefficients. So 6 square root 11 plus 9 square root 11, the square root 11 stays the same, you're just adding the coefficients. So 6 plus 9 is 15. Okay? All right, so we have square root of 2 plus square root of 2 minus square root of 10. So we're looking for identical radicals. The square root of 10 can't be simplified. If it could be simplified, we'd do that first, because sometimes you might actually find a similar radical by simplifying. But in this case, 10 is 2 times 5, so that can't be simplified any further. But what I do notice is I have a square root of 2 and a square root of 2, so those can be added together. So imaginary 1 in front of both of these, so that's going to give me 2 square roots of 2 minus square root of 10. All right, so you go ahead and try practice problems B and C on your own. And that's on page 534. Okay, on the first one, they were both like terms. So 1 minus 7 gives us negative 7, square root of 6. On the bottom, we only had 2 like terms because with this being the fourth root of, I think it was 7, let me double check, yeah. With this being the fourth root of 7, then we can't do anything as far as combining with the square roots of 5, or sorry, the fourth roots of 5. So this is really important. The only reason we were able to combine these is because they both were a fourth root of 5. If it had been a square root of 5 and a fourth root of 5, we wouldn't have been able to combine them. So they have to be identical in what's under the radical and identical in the type of root. So they're identical, fourth root of 5, And we have 6 minus 2, so that gives us 4, 4th root of 5, plus the 11, 4th root of 7. All right, sometimes a radical must be simplified before adding or subtracting can take place. So on these, we're gonna have to do a little bit of simplifying before we're gonna find anything that's capable of combining. All right, so we're gonna start with A and then we'll do B afterwards. All right, so we're taking the square root of 27. I know that there's nothing that will equal 27 as a perfect square, but what I can do is break it down. So I know that 27 is 3 times 9. 9 just happens to be a square root, or a perfect square, I should say. So I can take the square of 9, which is 3, and then what's left behind? This 3. Okay, now let's break down 75. So 75 is 3 times 25, and 25 just happens to be a perfect square. So if I take the square root of 25, that's 5, so that's on the outside. What's left underneath? 3, and I have this plus sign because we're adding them. And because we were simplifying, I just noticed we have a square root of 3, square root of 3, so that means we can combine them. So we're adding the coefficients, 3 and 5 is 8, and then you have square root of 3. All right, let's take a look at B. Okay, so I'm just gonna sort of move from left to right, simplifying this stuff. So square root of 36, I can actually take the perfect square of 36, so that's gonna give me a whole number of 6. For 48, I have, let's see, how can we break that up? I guess I'll just start with 2 and 24. I know that that's not going to give us a perfect square yet, but... Okay, so here's something I noticed. I have 4 2s, and then I have a leftover 3. So I'm taking the perfect square. So that means I can actually turn this into 2 times 2, so that equals 4. 2 times 2, that equals 4. So I can actually take the square root of, 4 times 4. If I were to combine it all together, it would be 16. So the square root of 16 is 4. And the reason I know I can do this is because I have 2 4s. So I know a 4 is going to go on the outside. What's left underneath the square root symbol? 3. Okay, so now moving on to the next one. 4 square root of 3, that can't simplify any further. And then square root of 9, can I simplify that? Yes, 9 is a perfect square. So that's going to give me the whole number of 3. Okay, so what I need to do now is go ahead and identify, do I have any like terms? So the first thing I notice is I have a 6 and I have minus 3. So my whole numbers I can go ahead and combine. So 6 minus 3 is going to give me 3. Now on these radicals, I have negative, don't forget your sign, negative 4 square root of 3 minus 4 square root of 3. So I have 2 of the same thing. So that means that because these have matching radicals, then I can combine them. So this is minus 4. Right now, just looking at the coefficients, I have minus 4, minus 4. So that's going to give me minus 8, negative 4 make negative 8, and then the square root of 3. And that would be the final answer. All right, so I have a little bit of erasing to do before we can do our practice problem, but I want you to go ahead and start. You're doing practice problem letter B, which is on the top of page 535. Okay. So this one's a little bit trickier than the ones we were doing because it had a little bit more work involved. So square root of 36 is 6. 3 times the square root of 24. You can actually simplify this one even though there's a number already on the outside. I broke it into 4 times 6. So 4 is a perfect square. If I take the square root of 4, it's 2. So remember, when you pull a number on the outside to a number that's already there, you multiply. So 2 times 3 equals 6. So that gives me 6. And then what's left under the hat? 6. All right. Then square root of 40, 4 times 10. Perfect square is 4. So if I take square root of that, it's 2. And then 10 is left under the hat. And then minus carries down. For the square root of 150, I did 10 times 15 and then broke it into 3 times 5 and 2 times 5. I noticed I have 2 5s underneath my radical, so I can pull that out. So the difference really between, like, say 4 times 6 is that because I know 4 is a perfect square, I'm taking the square root of 4. But here, the difference is I already broke it down into factors. So the fact that I see I have a 5 and another 5, you don't have to take the square root of 5 because I notice I have 2 of them. So when I pull the 5 out, I'm just pulling out the square root of what 5 times 5 would have been, which is 25. So anytime you notice, if you break it down all the way completely into factors and you're like, oh, I have 2 the same number and I'm taking the square root, then you don't have to take the square root of that factor. You're just taking that number out of the radical. So after doing that, I noticed I have two different numbers with the square root of 6, so that means I can combine them. So I have 6 square root of 6 minus 5 square root of 6, which is just the square root of 6, and then the minus 2 times square root of 10 did not simplify any further, so that's a part of my answer. All right, moving on. If radical expressions contain variables, simplify first and then add or subtract like radicals. So now we're throwing in variables. Okay. So remember, always start with your coefficients. Square root of 9x to the 4th. So 9 is a perfect square, so square root of 9 is 3. When you're doing variables, you're doing the exponent divided by the radical root. So 4 divided by 2 gives us x squared. Minus the square root of 36 is 6. I have x to the 3rd. So I can't do 3 divided by 2 without getting a decimal, which means I have to change it into factored form. So I'm going to just write up here x squared times x because I need to change the exponent into something that will divide by 2. So 2 divided by 2 gives me 1x. What's left behind? An x. Plus, once again, yeah, we can still do that. Once again, I have x to the 3rd, so I have to change that. X squared times x. So the square root of x becomes x, and then I have an x that's left behind. So by doing this, 3x squared we obviously can't do anything with, but notice we have the square root of x and the square root of x. So just like you would before, as if this was a number, you can actually have identical radicals with a variable as well. So the square root of x symbol is going to stay the same. The only thing we're doing is adding like terms in front of it. So what's going to happen is we're going to do negative 6x plus x, and then of course my radical symbol is going to stay the same. So I'm going to go ahead and write 3x squared because I know I can't do anything with that. So negative 6 plus x now becomes negative 5x because these numbers on the outside are variables, so they remain variables, just as the hat remain, or the radical, the part under the radical also stays the same. Okay? All right. So go ahead and try the practice problem on your own. I think I'm going to erase this to have more space for it. So go ahead and try on your own and then check your work with me after I have finished it. Okay, so x to the 3rd, I change to x squared times x. I take the square root of x squared. 2 divided by 2 is 1x, with 1x left under the radical. I can't do anything to this, so I just carry it down. Minus 8x square root of x. And then 3x squared of x squared, 2 divided by 2 gives me an x. So the x squared came out perfectly. It can't combine with anything, so notice it did just carry to the final answer. But we have like terms here. We have x square root of x minus 8x square root of x. So with the coefficients, 1 minus 8 gives me negative 7, and then x square root of x. Okay, so this one is just sort of a little more complex version of what we've already been doing, but we are dealing with now cube roots instead of square roots, so that's probably the main difference that we're doing. Okay. So the first thing we need to do is look at our coefficients. 54. That's going to be 6 and 8. No, wait. I always get those mixed up. 9. No, I was right the first time. I always get 54 and 56 mixed up on my timetables. I don't know why. Okay. Okay, I'm just going to break this down. So we got 50, 25, 27. And then that's 3 times 9. Oh, actually, that's all I need to do. Okay, that's going to work better because we are working in cubes. Okay, so this is 2 times 27. 27 is a perfect cube. So with that, then we're going to take the cube root of 27, which is 3. When I pop out the 3, I have to multiply it by what's already there. So that's going to give me 30. And then I'm not going to draw the rest of my stuff yet because I do have to take care of this p to the 12th. So 12 divided by 3 does work, so I don't have to do anything as far as factoring p to the 12th. So 12 divided by 3 gives me p to the 4th, and then what's left under, this 2 never got used, so it's still there. All right, minus, that minus sign is still gonna stay. 250, so we're just gonna make this easy. 25 times 10, and then that's 5 and 5 and 5 and 2. And I notice I have 3 5s. So since I broke this one down into completely a baseline of only factors, that's where I'm going to use the counting method. I'm looking for as many of the same number as this number. So I have a perfect set of 3 5s, which means I can take the cubic root. So I'm pulling out that 5. So these are gone now. I needed 3 of them. What's left underneath? This 2. Now before I write that, I want to go ahead and take care of my p to the 12th. So 12 divided by 3 gives me p to the 4th. What's left? That 2. So now let's look at what we have. We have 30p to the 4th square root of 2 minus 5p to the 4th square root of 2. So because the p to the 4 part is the same and the square root of 2, sorry, I said square, cube root of 2 is the same, then that means we can go ahead and finish solving. So I'm just doing 30p to the 4th minus 5p to the 4th, which is 25p to the 4th, and then the cube root of 2. All right, so that's it as far as section 8.3. Knowing that 8.3 was going to be so short, I decided to just go ahead and throw it into the same video as 8.4. So this video is still going to keep going, and we're going to start back at the beginning of example 1 with section 8.4. All right, objectives for 8.4, multiply radicals, divide radicals, rationalize denominators, and rationalize using conjugates. So this one's gonna be focusing on multiplying and dividing, whereas the last section was focusing on adding and subtracting. The product rule for radicals can be found on page 538. So I'm gonna go ahead and turn to that. All right, so it's in that lavender box where the book usually has all their rules. It shows you that if you multiply, and we've already learned this before, but it's just a review. If you multiply the same root and the same radical, so they're identical, then they can combine under the same radical hat, or you can separate them, vice versa. Numbers containing the same type of radical can be multiplied by combining their products. So let's take a look at our first example. Oh, I wrote the wrong number. All right, so when I have a radical times a radical, as long as the root is the same, so notice they're both 2, then all I do is just multiply what's underneath each radical, and that gives me my answer. So the square root of 10, okay? Now, this next one is actually a rule. Yeah, so if you look at the next rule at the bottom of page 538, it says if a is a positive number and the root of a, the square root of a times the square root of a, it's going to equal, basically, if you take the same root, the exact same root times the exact same root and radical, then what's happening is it just becomes the number that was there. Because if I were to do 13 times 13, multiply it together and have it under the square root symbol, if I take the square root of that, I'm just getting what I just multiplied under the root. So anytime you have the same exact root times root, then you just take away the root and whatever was under the root is your answer. Okay, so when you have numbers on the outside and numbers underneath, then the numbers on the outside get multiplied together separately from the numbers that are underneath. But this, when we start getting into more multiplication, it does involve more simplifying. So unfortunately, these problems are going to get a little bit longer than what you would think. So there's 2 ways you can really go about doing this. To make it less confusing, it might be easier to just go ahead and multiply the numbers on the outside and then work with your numbers underneath. So I'm going to go ahead and do 7 times 4, that's 28. And then here's what I'm going to do. Instead of writing 3 times 15, which is 45, I'm going to write 3 times 15, and I'm going to see what are the roots of 15. 3 and 5. The reason I didn't make it 45 is because I want the most simplified form. So by writing 3 times 15 and then breaking 15 down, this shows me, oh, wait a second. I have 2 3s. That means I can pull the 3 out because I'm taking the square root. So if I pull that 3 out, now I have to multiply 28 times 3. So now my answer is going to be 28 times 3, which is, I think it's 84, but I want to make sure that's right. I didn't bring a calculator with me. And I don't want to tell you the wrong answer. Yeah, it's 84. So 84. And then what's left underneath my square root symbol? This 5. Okay? All right. Okay, so we don't have anything on the outside, so I'm just going to focus on the inside. But once again, with the coefficients, I'm still going to use that 10 times 2. And then for the x's, I'm just going to add them together. So I have 1, because anytime you multiply variables, remember you're adding their exponents. So 1 plus 5 gives me x to the 6th. So now, with my coefficients, I'm going to break 10 into 2 times 5. And by doing that, I notice I have 2 pairs of 2's. So that gives me enough to be able to pull the 2 out. So I know I have a 2 out, so the 2's go away. And then for the coefficient, I still have a 5. So we're going to get to that in a second. Moving to the x to the 6th, can I do 6 divided by 2? Yes, I can. So that means the x's are going to completely come out of the radical. So 6 divided by 2 gives me x to the 3rd. I'm going to draw my square root symbol. What's left? 5. All right, so you go ahead and try practice problems C and E on your own. C and E. All right, with the first one, I broke it into 5 times 10 under the radical. 10 breaks up into 2 times 5. I have 2 5s, so I take the 5 out, and the 2 is left behind. And the second one, I did the coefficients first, 2 times 6, but then I broke 6 down into 2 times 3, and I noticed, oh, hey, there's 2 2's. So I can pull the 2 out. So I have 2 on the outside, and then for the x to the 4th, 4 divided by 2 is 2. So x squared, and then what's left behind? The 3. If a is a positive number, and we already talked about this from the previous example problems, if a is a positive number, a times a equals a. So anytime you have the same thing underneath the radical, then it's going to be the same answer. Now, don't get confused by the fact that this is squared. 7 is on the outside, so it still gets squared. So 7 squared is 49. But the square root of 3 times the square root of 3 becomes just 3. So 49 times 3 is going to give me 147. Okay? All right, and I did have a practice problem for this one. Let me take a look at it and see if I feel like I really need you to do it. Yeah, you can go ahead and do it. I mean, it won't take me very long to work through it and then go over. Okay, so if you did it, 2 square root of 7, so the 2 gets squared, which is 4. Square root of 7 squared becomes just 7, so 4 times 7 equals 28. All right, so we're still practicing, but this time we have cube roots. And notice they both are cube roots. This wouldn't work unless they both have the same number root. So I'm going to write 6 times 18, and then I'm going to break 18 down into 3 times 6, and I notice that gives me 2 6s. So that means I can pull the 6 out. What's left behind? The 3. All right, go ahead and try the practice problem on your own. Okay, so actually I need to go back on that problem I did earlier, because I did the square root, not the cube root. Don't make the same mistake I do when you take your test. So I'm going to finish this practice problem, and then we're going to go back and we're going to fix this. Okay, so on the practice problem, I notice I have, by breaking it down into 10 times 50 and then 2 times 5, for 50, 5 times 10, and then 2 times 5, I notice I have 3 5s, so I can pull out a 5. What's left behind? I have a 2 and I have another 2, so just multiply those back together, and that gives me 5 times the cube root of 4. All right, so let's go back to this first problem because I made a boo-boo on that. It's the cube root, and I accidentally accounted for the square root. So this is actually a good relearning moment as far as when you take a test. Always pay attention to what that root is, because I overlooked it, which means you could possibly overlook it too. So with 6, I'm actually going to break it down into 3 and 2, and with 18, 3 and 6, 2 and 3. So I have, by doing that, 3 sets of 3. I'm looking for 3 of something. So that means I'm pulling out a 3. What's left behind? I have a 2 here and a 2 here on all my factors. So 2 times 2 brings it back to 4. All right, use a distributive property is identified and simplify as much as possible by combining like terms. Okay, so if you remember when we distribute with variables, anytime you have a number on the outside of parentheses, you multiply it times everything in the parentheses. So we're going to do square root of 7 times square root of 7. What's the rule? Right. It's just going to become 7. Square root of 7 minus square root of 3. Because 7 and 3 can't break into any more factors, then that means I know I can just go ahead and put them both under the radical sign because they're not going to simplify any further. All right, square root 11y times the square root of y. So with this, 11 is here and y is here and y is here. So that means that when I multiply this, the 11 is not going anywhere. Okay, so the 11 is still going to be stuck under the radical. But if I do y times square root of y times square root of y, that means the y is going to come out. So the 11 is still there, but the y gets to release. Minus square root of 11y times the square root of 2, or negative 2 square root 11. So this time I have an 11 and an 11. So that's going to come out of the radical. Anytime you pull something out and multiply it times a number that's already there, or sorry, you have to multiply it times the number that's already there. So if I pull the 11 out, it's going to multiply times negative 2. So that's negative 22. What's left behind? Square root of y. And that can't simplify any further because they're different underneath the radical sign. Okay, so on this one, we have a binomial times a binomial, which means we are going to use the FOIL method. So first, square root of x times square root of x, what's that going to become? Just x, because same thing times same thing. Square root of x times the square root of 3. So negative square root of 3. So they're both under the radical, which means they're both going to stay under the radical. Inside, positive square root of 5 times positive square root of x. They're both under the radical, so they stay under the radical. Okay, then positive square root of 5. So last, positive square root of 5 times negative square root of 3 minus square root of 15. That can't simplify any further, so it stays there. And I don't think we can simplify any further. I'm just going to double check to make sure I'm not telling you wrong. Yeah, that's our final answer. There's nothing that we can simplify because nothing under the radical is identical. Okay, so you go ahead and try letter B on your own. I might want to, yeah. There. Okay, so square root of 2z times square root of z, the z pops out, the 2 stays behind. Square root of 2z times 7 times the square root of 2. So square root of 2 times square root of 2 pops out as a 2. So 2 times 7 becomes 14. What's left behind? The z from here. So times square root of z. Okay, FOIL method. First, square root of 2 times square root of 2 becomes just 2. Square root of 2 times negative 6. So negative 6 is a whole number, so it will stay on the outside. So minus 6 times square root of 2 on the inside, plus 6 or positive 6 times square root of 2. So the 6 is on the outside because it is a whole number. Then last, positive 6 times negative 6. Negative 36. Now by doing this, I noticed that I have like terms. Square root of 2, square root of 2, minus 6 plus 6. So what happens to that? They actually cancel each other out. So that gives me 2 minus 36. So that's going to give me negative 34. Okay, letter B. Okay, so on this one, notice there's a squared sign. So what this means is this binomial twice. So I'm going to actually take away that 2 and just add in another 5x plus 4. Oh, sorry, square root of 5x plus 4. So now we're going to FOIL it. So square root of 5x times square root of 5x becomes the same thing. That's underneath the hat. So 5x, just remove the radical sign. Square root of 5x times positive 4. So the 4 is going to be on the outside, 5x on the inside. Positive 4 times square root of 5x. So plus 4 square root of 5x. 4 is on the outside, 5x underneath. Then 4 times 4 is positive 16. Do we have like terms? Well, let's find out. So we have 5x and 5x, so we can add those. Okay. But the 5x and the 16, they're not like terms, they can't do anything. So it looks like we have a positive 4 and a positive 4, so that becomes 8. So I'll have 5x plus 8, square root of 5x plus 16. Final answer. So on that one, since you saw 2 examples that were somewhat similar, I know it says to do a practice problem. I'm going to go ahead and skip that one. I don't feel like it's super necessary. If you're not sure about this example problem, just go back and rewatch me going through the 2 examples that we just did. All right, the quotient rule for radicals. If a to the root power of n and b to the root power of n are real numbers and b doesn't equal 0, then a to the root of n over b to the root of n, you're basically just combining them under the same radical. And we've done this rule before, so we're just building on it. So the reason this is a good rule to know is because sometimes you can actually divide them. If you put them under the same radical sign, you're like, oh, wait a second, I can do 15 divided by 3. There's greatest common factors there. So 15 divided by 3 is 5. So the answer, if it can't simplify out of the radical sign, then it's just whatever you get simplified, so square root of 5. Okay, so I can actually do some simplifying here. 75 divided by 3 is 25. Remember our rules for variables. If I have the same variable on the top and the bottom, you just subtract the exponents. 3 minus 1 gives me x squared. Now this is all still under the radical, but notice what this problem does, unlike the last one. Can I take the square root of 25? Yes, I can. It's 5. Can I take the square root of x squared? Yes, I can. 2 divided by 2 gives me x. So this one actually simplified into a non-radical number. All right, so you go ahead and try practice problem letter B. This is example 6, page 540, letter B. Okay, so square root of 48 over square root of 6, I put under the same radical. 48 divided by 6 becomes 8 under the radical. 8 can be simplified. Don't leave it that way if it can simplify further. So 8 is 2 times 4. 4 just happens to be a perfect square. So if I pull out the 4, take the square root of 4, it becomes 2. What's left underneath? 2. All right, we're doing the same thing we did before, except for this time we have a cubic root. Okay, so 250 divided by 2 is 125. Can I take the cube root of 125? Yes, I can. The cube root of 125 is a perfect whole number 5. Final answer. It is sometimes easier to work with radicals if the denominator is not expressed as a radical. By multiplying by the radical expression in the form equivalent to 1, this will not change the value but allow the radical to be removed. So what we're dealing with now, remember when we had a rule that said you can't have 0 on the bottom? Well, having a radical on the bottom isn't necessarily an error to the calculator, but it's not good. We don't want radicals on the bottom. So just think, we don't want zeros on the bottom, we don't want radicals on the bottom. So how can I get rid of a radical? Well, if you remember the rule, if you multiply the exact same radical times itself, it goes away. It becomes a whole number. So in order to get rid of this radical on the bottom, what I'm going to do is multiply by a number that takes away the radical but doesn't change its value. So anytime you want to do that, multiply by something that doesn't change the value, you want to get it into the form of the value of 1. So what you want to do is multiply by whatever that radical is in the form of 1. The radical, the square root of 3 divided by the square root of 3 is 1. So by multiplying by the square root of 3 over the square root of 3, I'm not changing the value of this, this fraction. I'm just going to change the way it looks. So top numerator multiplies, that becomes 5 square root of 3. On the bottom, square root of 3 times square root of 3 becomes 3. So now the radical is on top and it's not on the bottom. So it's okay to have radicals on top. We just don't want them on the bottom. Okay, so on this one, I'm going to actually switch it to the separate radicals, one on the top, one on the bottom. So that way, when I multiply, I'm going to multiply by the exact same on both top and bottom. So on top, then I get, on top, this is going to involve a little bit more. So 2 times 45, and we'll deal with that in just a second. On the bottom, square root of 45x times the square root of 45x becomes just 45x. Now on top, I need to do a little bit more because I don't know if I can simplify this further. So 45 is 5 times 9. And the way this appears, I'm not going to be able to simplify that any further. Okay, actually there is one part that I can pull out. I can pull out the 9. So if I take the square root of 9, that becomes 3. The 2 and the 5 are still there. So that multiplies to stay under the radical as 10. Then on the bottom, I have 45x. Now it looks like we're done. But not quite, because what do you notice? 3 and 45 can both divide by each other. So 3 is going to go away, and I'm going to divide 45 by 3, which is 15. So that gives me square root of 10 over 15x. So these problems can sometimes be solved pretty quickly, and sometimes they take a little bit more work. So it just depends on what your problem is. In this one, it took a little bit extra work, but notice the goal was to get rid of the radical on the bottom, and that's what we did. Okay, you're doing practice problem B. I'm just erasing this so I have space to do it on. Okay, so on this one, you really could have taken several routes to get there. I went ahead and noticed, oh, hey, 3 and 18 can both divide by 3. So I simplified before getting rid of the radical. You could have just multiplied times square root of 18 over square root of 18 and then simplified later. So it really doesn't matter which one you did first. The idea is that you just want to make sure that you did simplify and you did get rid of the radical on the bottom. As a general rule, simplify a radical expression first and then rationalize the denominator. Okay. We are getting there. 3 more problems. Well, examples. Okay. So Okay, so something that we're going to do, I don't know if I want to do it this way or not. It might be more confusing. I think we're just going to do this the way we've been doing it because I feel like that the method the book is teaching might be more confusing than it will to just keep doing it the way we were doing it. So we're just going to multiply the top and the bottom by the same root that's here. So that's going to cause, oh, actually, you know what? Yeah, it's still going to work, I think. No, wait, it's not. Is it? Yeah, I'd have to multiply by 3 of them. Okay, take that back. We'd have to multiply it by 3 of these in order, because it's a cube root, not a square root. Okay, so on this one, it is going to be a little bit more confusing than what we did before. See, when we're doing a square root, then if you multiply the square root twice, because it's square 2 times, then it takes away the radical. But when you have a cube root, you'd actually have to multiply it 3 times in order to take it away. So to avoid having to multiply it by the cube root of 9 over the cube root of 9 two more times, what you want to do is try to multiply it by something that will cause what's underneath this hat, underneath this radical, to go away. So right now, if I break 9 into factors, I have 2 3s. I need 3 3s in order to remove the radical sign. So how do I do that? By multiplying by the cube root of 3. So we're going to do that on both the top and the bottom. So on the bottom, if I do 3, well, really you could just look at it as 9 times 3 is 27. The cube root of 27 is 3. On top, 7 times the cube root of 3. Can't simplify any further, so that would be your answer. All right, letter B. All right, so right now I have 1 5. I need 2 more 5s to get to 3. Okay, so that means I need to multiply it by the number that will give me 2 more 5s. So 5 times 5 is 25. So it's this cube root of 25, and we multiply by the same number on the top and the bottom. So on the bottom, 5, 5, and 5 means that if I take the cube root of 5 times 25, that's 125. So cube root of 125 is 5. Then underneath here, we're actually multiply them because they're both under the hat, or under the radical sign. These are all primes, so they're not going to be able to simplify. So I'm going to actually have to do 25 times 11 and put it under my radical. Fortunately, I left my calculator upstairs, so I'll have to do it the old-fashioned way. Huh. I think I did that right. Yeah. Okay. I'm gonna double check the book and make sure. Yep, that's right. Okay, so that would be our final answer. All right. Since this one is a little bit tricky, I think I do want you to go ahead and do the practice problem. I was kind of debating, just because I know this video is getting kind of long, if I wanted to have you do it or not, but go ahead and try it, just because I feel like this is harder than doing the square roots of removing the radical. All right, so you're doing letter A. All right, so on this one, I have 25, which is 2 5s. I need to add another 5 to that. So if I multiply by the cube root of 5, then I now have 5 times 5 times 5, so I can pull that 5 out on the bottom. No more radical. On the top, 3 on the outside times the cubic root of 5 on the inside, and that can't simplify any further. To rationalize a denominator that is a sum, you must multiply the top and bottom by opposite expressions. So our goal in this is still to have no radical on the bottom, but you can't just multiply by a single radical when you have a system going on, because this is an expression, so I can't just multiply by the square root of 2 because I have the square root of 2 minus 1. So when you have an expression, what we have to do is multiply by another expression. So the way to get rid of your square root of 2 is to multiply by the opposite expression of what is here. So if we multiply this by, typically, let's see, I think it should still work if we, I was trying to decide if I wanted to reverse this into -1 plus the square root of 2. We're going to try this. I think it's going to work. But you want to have the same expression, but switch your signs. I'm going to try it on switching it on the middle sign as opposed to on the sign of the actual square root symbol. So if this doesn't work, we're just going to go back and try it again. But the idea is that whatever this expression is, you multiply by the opposite of it. So square root of 2 minus 1, we're going to multiply it by the square root of 2 plus 1. And whatever you do to the bottom, you have to do to the top. Okay? All right, so we're going to FOIL the bottom. Square root of 2 times square root of 2 becomes just 2 because they're square roots. The hat goes away when it's the same number. Square root of 2 times +1 is positive square root of 2. -1 times -1 times the square root of 2 is negative square root of 2. And then -1 times +1 is -1. Now on the top, square root of, I'm going to put a parenthesis around that because we are foiling. Square root of 2 times square root of 2 becomes 2. Square root of 2, so the outsides, square root of 2 times 1 is plus square root of 2. Inside, 5 times square root of 2. And then 5 times 1. All right, now we got some simplifying to do. So on the bottom, the goal was to get rid of the square root. And notice what we have. Positive square root of 2, negative square root of 2. So those cancel each other out. What am I left with? 2 minus 1, which is 1. So all I'm left with is what's on top here. So on top, I have 2 and 5. So that can simplify to 7. And then I have the square root of 2 plus 5 square root of 2. They have the same square root, which means I can add them. 1 plus 5 is 6. Square root of 2. Okay? Okay. Yeah, I'm going to erase this so I can do the second problem. Okay, so I'm going to multiply this whole thing by the opposite. So I'm going to do 2 plus the square root of x on both top and bottom. So on top, 7 times 2 is 14. 7 times square root of x is 7 square root of x. On the bottom, I have to FOIL because I have a binomial and a binomial. 2 times 2 is 4. 2 times square root of x is 2 square root of x. Negative square root of x times 2 is negative 2 square root of x. And then negative square root of x plus positive square root of x becomes minus x, because they cancel each other out with the square root of x times square root of x. All right, so we have some simplifying. Top, I can't do anything, so I'm just going to write my final answer there. 14 plus 7 square root of x. On the bottom, 4, there's no other whole number, so I can't do anything there. 2 square root of x minus 2 square root of x. Those cancel each other out. Minus x. So on the bottom, I'm left with 4 minus x. Final answer. All right. So I know that we are almost done, and I know that this video is getting kind of long because I had to combine both sections, both 8.3 and 8.4 into one. So we're going to skip the example problem on that. I feel like doing 2 of them should have hopefully been enough to kind of give you an idea of how to do it. And then we're going to move on to example 11 and be done. Okay. So this one I don't think is as complicated as example 10. Notice that what we have here is an expression on top with just a number on the bottom. So that means if I wanted to, I could actually break these up into 2 separate fractions and simplify. So let me decide if that's the way I want to do it or not. So there's really 2 ways we can go about doing this. Okay, I take that back. We're going to actually keep it all over 25, and we're going to start by simplifying what I know we can simplify, which is square root of 75. So we're going to ignore the 15 and the 25 for right now. We're going to focus on simplifying the square root of 75. So 3 times 25, and I noticed 25 is a perfect square. So 15 stays the same, minus sign stays the same. Square root of 25 is 5, so that pops to the outside. 3 is underneath. On the bottom, 25. Now, the reason I was trying to decide if I wanted to break it into fractions is because I automatically noticed, hey, 15 and 25 both have a similar factor. Well, by simplifying the square root of 75 first, that also shows me, hey, 15 minus 5 square root of 3. I can actually factor out, if you remember factoring works with radicals as well as it does variables. So I can factor a 5 out here. So that's what I'm going to do. I'm going to factor a 5, and then I'm going to write what's left behind. 15 divided by 5 is 3, minus. If I take away the 5, what's left behind? This square root of 3 symbol. And then I'm going to put it over 25. So now by factoring out that 5 and 25 are both divisible by 5. So now that 5 can go away. So that leaves me with 3 minus the square root of 3 on top. On the bottom, 25 divided by 5 is 5. Okay, so I know that I went through a lot of information in this video. Please feel free to go back and watch it again. Do some more practice problems if you feel like you need them. The odd numbers have the answers in the back of the book, as I always would assign suggested homework. And if you have any questions, please let me know. I know you didn't have as much time to learn chapter 8, even though it's shorter. It doesn't make it any easier. So just reach out to me. Your homework for this assignment is due next week, and your test is due next week as we are approaching the end of the semester. So if you need anything, just let me know and I'll get back to you. All right, bye.